I'm going to go ahead and start class. We are on 4.6. That's the assignment that is due tonight. 4.6, and 4.6 is on the derivative of exponentials. So the derivative of exponential and logarithmic functions. Okay, so if you recall for 4.5, 4.5 wasn't about calculus at all. In fact, we just reviewed a bunch of stuff from secondary math 3 regarding exponential functions and logarithmic functions. And so today, the big idea is to talk about how to find the derivative of logarithmic and exponential functions. And then we're going to have to add these to our flashcards as well. Okay, so let's consider if I have y equals 3x squared plus 4x plus 5. Now, when I take the derivative of this, what do I do? Yep, exactly. Is this an exponential function? No. What kind of function is it? This one is quadratic. Yep. With the exponent is squared, and because the degree of our function, the highest exponent for the function is 2, so it is quadratic. So in fact, all polynomials can be solved by using the power rule. So polynomials can be solved, polynomial functions can be solved by using the power rule. Can be differentiated. Can be differentiated using the power rule. Now, we do have a concern about this other group of functions, this other function family called exponential, where I have y equals, I don't know, 3 to the power of x. Now, it seems like we could do the same thing, just, multiply the base. If we wanted to find the derivative of this, we would multiply our base with our exponent. That would give us 3x. And then we need to subtract 1 from our exponent, which would be x minus 1. And the answer is that does not work. That does not work. We cannot do it this way. So exponential, it turns out that with an exponential, that will not tell us our instantaneous rate of change for some value of x. So there's another way of solving for this. This method doesn't work. So we're going to use a different method. Now, if we have something like y equals e to the x. We talked about e before. What is e? What is e? And yeah, it's about 2.72, something like that, ... forever.
Constant.
What's that?
Isn't it called something constant?
It is, some people call it Euler's, like Euler's number or something like that. And maybe that's what the E stands for Euler, or maybe not. I don't know. But yeah, we have this value of E that represents, it's a value that we use when we compound continuously. We're not compounding once a year. We're not compounding twice, or even every month, or not even every second. We are compounding continuously. We converge on this value of e. I want to find the derivative of this, e to the power of x. So how do I do that? Well, let's go back to this idea of the limit. The limit as h approaches 0 of, remember our function of f of what is the rest of the function? F of
X plus h minus fx.
all over.
H.
Yep. And so my function is this e to the power of x. So I'm going to rewrite this as e to the power of x plus h minus e to the power of x all over h. Now, one thing that we haven't really discussed, and it gets into a higher level of math, and the way that we're going to show what this limit is we need this other piece over here of what happens with the limit as x approaches 0 of h approaches 0, sorry, of e to the power of h minus 1 over h. Now, I'm going to graph this instead of going into another level of math. I'm going to graph this so we can see what we converge on before we integrate that into our function over here. So I'm going to go to Desmos. And I'm going to type in our function of y equals, I'm just going to use x, e to the power of x minus 1 over x. And we want to know when, in this case, x approaches what? 0. So when we converge on x approaches 0, we get what? What are we converging on?
1.
Yeah, we're converging on 1. Before it becomes undefined, from either direction, we're converging on y equals 1 on both sides. Okay. So we're going to have to use this piece here to show what this converges on. So I'm going to use our law. We have one law that says that if I have a to the power of b times, this is a law of exponents, a to the power of b times a to the power of c, then that becomes what? Becomes what? Yeah, a to the power of b plus c. Can I do the same thing over here, but backward? Okay, so that's going to give me, I wanted to use right there we go. I have the limit as h approaches 0 of e to the power of x times e to the power of h minus e to the power of x over h. Any suggestions of what to do at this point? Yeah, can't I factor an e to the power of x out?
Yeah.
So that's going to give me, so I have the limit as h approaches 0 of e to the power of x times e to the power of h minus what? 1 over h. Now, remembering one of our laws of limits is that if I have, what did you call it, Thomas? It's the limit of a product is the, do you remember that one? The limit of a, or how about a limit of a, yeah, the limit of a product is the product of two limits or something like that?
Yes.
Okay, so that would give us the limit of, as h approaches 0, of e to the power of x times the limit as h approaches 0 of e to the power of h minus 1 over h. Well, we graphed this already, and we found that that is when h approaches 0, what do we get? What did we find that this becomes? when h approaches 0. It becomes 1. So this would be the limit as h approaches 0 of e to the x times 1, which becomes what? Yeah. We get e to the x. Because I can't even plug any, I can't plug an h in there, so that is my answer. My answer for this is e to the x. Yeah, huh?
Wait, e to the x is the derivative of e to the x?
Yeah. Crazy, huh? Y equals e to the x. Let's consider this. This is sort of a cool idea. That let's graph this. Let's go ahead and graph this where we have y equals e to the x. Now I'm saying then that our function of e to the x, the derivative of this is itself, which means then that this point right here, where x is 0, y is 1, has a slope of, it has a slope of 1. The y is 1 for position, and my slope is 1. So that means if this represented a location, then my location would be 1, but my velocity would be 1. Yeah, that's so crazy. Or over here, let's look at this point right here. Let's say, I don't know, at this, let's find something that's a little bit easier to maybe to eyeball. I don't know, almost, I can't quite get a perfect answer, but let's say approximately, right? When x is approximately 0.7, then our slope is approximate. So our y is approximately 2, but the slope is approximately 2. It's the same. It is the same. Now I can only think of one other function where the derivative is itself, and that is y equals 0. Because the derivative is what? 0, yeah.
Okay. So is e to the x the only exponential? No. Is e to the x the only exponential that is its own derivative?
Yes.
Okay.
In fact, we'll have to use another rule for the finding the derivative of other exponentials. But e to the x, it turns out it's its own derivative. And I can only think of one other case where the function is its own derivative, and that is when y equals 0. That is just crazy. In fact, I would encourage you to look this up on Khan Academy. You have Saul Khan that gets really excited about this. It's like, this is just phenomenal. So if you want to see a proof on this, watch it from Saul Khan, especially with how excited he gets about it. Okay, so we're going to, let's look at some examples then. If I want to find the derivative of y if y equals e to the negative x. Any ideas of what the derivative of this is?
Could it be e to the negative x?
Close. E to the negative x. Close. Thomas?
Would it be negative?
Why is it negative e to the power of negative x?
Because there's a function inside of that.
Yeah, this is the chain rule.
Yeah.
Right, Bentley? If I have e to the u, then the derivative of e to the u is e to the u. But I have a function inside of another function, which is negative x. So this would be our, if I have y equals f of g of x, then the derivative of that using the chain rule, Bentley, is what? The derivative of the outside function times
Derivative of the inside function.
of the derivative of the inside function. Yep. So we're going to take the derivative of the outside function, which is just e to the u. So e to the u. And now we have to multiply by the derivative of the inside function, which in this case, the derivative of the inside function, the derivative of negative x is? Bentley?
Derivative of negative x is -1.
Yeah, it's -1. That's -1. So that this becomes your answer. Good with that? Okay, we have to use the chain rule on that one. All right, let's do another one. So I want to find, why not capitalize? I want to find dy dx of, we'll do y equals e to the 2x minus 1. So dy dx equals what?
Is it 2 times e to the x?
2 times e to the x. There's something wrong with this part. Recall this part here of the chain rule. What does the inside, what do we do with the inside?
Oh, you keep it the same.
We keep it the same. Yep. So the inside should be what?
2x minus 1.
Yeah, it's just 2x minus 1. Yep. Ken, are you good with that?
Yeah.
Okay, let's do another one. If I'm going too fast, let me know. I always think notes are a great way of getting repetition. You go back to your notes, you cover over the answers, and then you look at it and say, what's the derivative of this? Okay, let's do another one. So I want to find d dx if, I'll just say our function. Our function equals e to the -3 over x. Jacob, do you have it? Do you know how to do it?
Not really.
Okay, so we have to use the chain rule, right? Because we have a function inside of another function. If you consider that y equals e to the u is our outside function, then the inside function is -3 over x. And if we're going to use the power rule for the inside function, I think it's helpful if we rewrote this using our laws of exponents. So wouldn't that be the same thing then? Jacob is writing -3x to the power of -1.
Yeah.
Okay. So let's use the chain rule. The chain rule is really important. We need to remember this. If we have some function which is a composite function, a function inside of another function, then how do I find the derivative of that, Jacob? We take the derivative of the outside function times The derivative of the inside function, yeah. So the derivative of the outside function is what? Itself, right? The derivative of e to the x is just e to the x. So we have our derivative then, d dx, is going to be e to the power of negative 3x, right? That's just the derivative of the outside function. But we have to multiply it by the derivative of the inside function, which is here, Jacob. That looks to me like the power rule, because we just have a polynomial. Jacob, what is the derivative of this polynomial? So the power rule says if I have a to the power, a times x to the power of n, then using the power rule, I get what? A times n times x to the to the power of n minus 1. Yeah, that's the power rule. So we have to do the same thing with this. If we're going to take if we need to multiply by the derivative of the inside function, then we need to figure out what that derivative is of that inside function using the power rule. So what does that give me? Jacob? So times. So don't we, using our power rule, don't we take negative 3 times what? Times the n, which is what? In this case? Yeah, negative 1. Times x to the power of? Negative 1 minus 1, which is negative 2. Yeah, there you go. Yeah, to clean that up, we could do d dx equals e to the power of negative 3x. And then we have a negative times a negative, which is a positive. So that'll give us maybe a 3 here, a 3 here. And then we have a negative exponent, so we could move that to the denominator. Let me make sure that 3 looks better. Move this over. So we have a 3 here. And then we have this x to the power of negative 2, move that to the denominator. So that gives us x squared here. You okay with that? Mm-hmm. If this was free response, I don't want you to go here. Actually, we could even move this to the denominator because that's negative. Just stop here, stop here if it's free response. Okay, moving on. Here's my next example. D dx times x squared times e to the power of negative x. What does this mean? Yeah. If this was the derivative, it would be equal to, right? It would be equal to, equal to if it was the derivative. I don't want it to be equal to because I want you to find the derivative. So d dx times, or we just say d dx of, right? D dx of x squared times e to the power of negative x. Anna, I see 2 different rules that we're going to have to use here. Can you see those? Can you see them as well? We do have to use the chain rule because we have a function inside of a function. I agree with you. What else? We have to use the product rule because I have here a function times another function. Anna, do you see it?
Yeah.
Okay. Anna, do you remember if I have a function times another function, how to take the derivative of that? So we do the first function times plus. Yeah, I'm just gonna, you said it right, but I'm just gonna write it a different way. The second times the derivative of the first, yep. You said it correctly. I just want to make, I just am used to writing it that way. Okay, and then we also have the chain rule as well. Okay, so let's write these out. I don't know if this helps to write it out this way. I don't think I've ever done this in this class, but I'm going to do it anyway, just as a strategy, one strategy you can use to so that you don't miss anything. What is f of x? Yeah, it's x squared. I agree with you. What is f prime of x? Yep. What is g of x? What is the derivative of g of x? So this is, it's the chain rule. So we have, with the chain rule, since we have a function inside of another function, the chain rule is the derivative of the outside function, which is, if this is just e to the power of u, then the derivative of e to the u is just e to the u. So it's the derivative of the outside function of e to the negative x times the derivative of the inside function. This is the inside function. What's the derivative of negative x? What's the, it's just, yeah, just negative, it's -1. I didn't write it. Let me try that again. It's negative, it's just -1. Okay. So let's follow our pattern here. Make sure that we don't miss anything. So we have d dx equals, we take our f of x, which is x squared, times the derivative of g of x, which is right here. I'm just going to put the negative in front, if that's okay. Times negative e to the negative x. Plus, I see I don't have not enough room. I don't know if I should just move it down a little bit or move everything over. Let's just do that. But Mr. Hall, that's not fair. I don't have that option. What are you going to do? All right, so we took our f of x, which was x squared, times our g prime of x, which is here, plus our g of x, which is e to the power of negative x, times our f prime of x, which would be 2x. We just line everything up. It's more of a, the way we set it up, we can create a plug and chug if this is still confusing. So plus our g of x, which was e to the power of negative x, times our f prime of x, which was 2x. And if this was a free response, stop there. If it's not a free response, if it's multiple choice, my guess is that this would be in the front. Sometimes they move for multiple choice, they'll move, if it's a negative exponents, they'll move that to the denominator, this one as well. So they could certainly have this as one of the choices. Or they could have something like this, negative x squared over e to the x plus 2x over e to the x. Thomas, how do you feel about that? Does that look the same? Yeah, so they may have it like this if it's multiple choice. Okay. So what's one of our new flashcards?
The limit is x approaches 0 to h minus 1 over h equals 1.
Oh, no, you don't have to memorize that. You're talking about what we graphed over here.
Yeah. Sorry.
I'm actually glad yeah, that's sort of cool. You memorized that. No, you will not need to know this for your AP exam. What you do have to have memorized is the derivative of e to the x, which is e to the x. It's the same. You just have to remember the chain rule and the product rule and the quotient rule and all the other fun stuff. Okay, now Bentley asked, is this the only exponential where the derivative is itself? And unfortunately, the answer is yes. So that means we have to come up with a new rule for all of our other exponential functions, which will become flashcards. So if I have, in fact, the other flashcard, I'm not going to show a proof of this. You can certainly find a YouTube video that will give you a proof on this. If I have y equals a to the power of x, the derivative of this is going to be a to the power of x. It's the same thing. Oh, Mr. Hall, you lied to us. You said that there wasn't the same, that there were no other exponential functions where the derivative was itself. But you're right, because there's another piece to this. It's ln of a. So this is another one we have to have memorized. And that takes care of all of our exponentials. Does that mean we've taken care of all the main ideas for today? Yeah, we still have logarithms. We still have to do logarithms. All right, so we're going to do some problems using this. So we have two flashcards now. We have the e to the x, the derivative is e to the x. We also have, if we have some base here, so a to the power of x. The derivative of a to the power of x is a to the power of x times natural log of a. Yeah. So what would be the derivative then of 2 to the power of x?
Well, it would be 2 to the power of x and the logarithm of 2.
Yeah. This would be 2 to the power of x times ln.
Natural logarithm.
Yeah, I just call it ln. I'm lazy. Ln of 2. There you go. It is the natural log. You're right. It is the same thing as log base e.
You have to use our calculator for this.
No, we're not. Are we going to use our calculator today at all? I don't think so. I don't think so. So we have, let's do another one. Another. So these we want to find the derivative, right? So I have f of x equals 2 to the power of 3x. Who are you going to still? Carter. Carter, you are being summoned by the counseling center. That is not cool. You're going to lose out on precious calculus.
Thanks.
All right, so what do we get? Or do you want some think time?
I got 6 to the power of 3x.
6 to the power of 3x.
To the natural logarithm.
Is that how we do this? Is this the power rule? We only use the power rule for what? For polynomials. Is this a polynomial? Do we know what a polynomial is? A polynomial.
I do the power rule.
How did you get 6?
If when you do the chain rule, you get
Oh, okay, wait, then let's, so back up. What did you do first? Let's do it in steps.
So from there, just get the derivative of that is 2 to the 3x
Okay,
natural logarithm of 2 times 3,
okay.
which I then.
So you multiply this and this to get 6 times 3 to the power of x times ln of x, ln of 2.
Yes.
Can you do that? Is that allowed to multiply this 3 to this 2? We have a law that says, we do have a law of exponents that says if I have a to the power of b times a to the power of c, what do? I have a to the power of b
Times C.
plus c. Is that right? Okay. I also have one that I have a to the power of c times b to the power of c. I can rewrite this how? A times b to the power of c. We do, so I have a law that says if I have the same bases, I can add the exponents. I have a law that says if I have the same exponents, I can multiply the bases and keep the exponent.
So 3 has to stay separate.
Yeah, because 3 is to the power of what?
1.
It's to the power of 1. And the 2 is to the power of 3, to the 2 is to the power of 3x, and 3 is to the power of 1. So we don't have the same bases and we don't have the same exponent. So there's nothing we can do to put those together.
That was the one thing I was questioning, so it was allowed or not, so.
Yep. So Bentley, what you're saying is that I belabored the point, saying, I got it, Mr. Earl, I got it. Yeah, so this is the best we could do. I'm fine with this. But the best we could do is maybe, I do get a little bit nervous when we had this 3 and the 2, you know, does the 3 go in the log or is it out of the log? Remember, if it's in the log, it's horizontal for as far as a transformation. And if it's to the log, then it's a vertical transformation. So we're looking at 2 different concepts. So the best we could do is move that to the front. So we'd have 3 times 2 to the power of 3x times ln of 2, but we cannot combine those. I got it, Mr. Hall, I got it. Leave me alone. Yes, Bentley. Yes.
I was wondering why there's like a 3 at the end. How did you get that?
Oh, because we had to do the chain rule. So look, let's consider this back up here. I have 2 to the power of x. Here I have 2 to the power of 3x, which means that this is a function inside of another function. So the first thing we did is we took the derivative of the outside function, which is this piece here, times the derivative of the inside function, which is that piece there. So Bentley, I was mostly doing that explanation, not necessarily for your benefit. I know that if you're confused about it, I guarantee you there's other students in this class that are confused about it as well.
Okay.
I would say, all right, let's see a show of hands. But people feel intimidated with math and they feel that if they don't get it, they're dumb, but that's not true. I did not, math has been really difficult for me I had to earn through blood and sweat. I had to earn all of the math I know. I wish math came easy to me like it does with Thomas and with Bryn, but math, it never came easy for me. I had to work for it. I am convinced we learn through repetition because that's how I learned math. I learned math with lots and lots of repetition. I had a teacher that said, okay, do every other problem, do every 5th problem. I did every problem because that I knew I needed that repetition. All right, let's do another one. Let's do another one. Same thing, we're trying to find the derivative. I have y equals 3 times cotangent of x. Mr. Hall, why? Exponentials with trigonometry, with an exponential function with a trigonometric function. I want to find the derivative. Do you see the chain rule? Kana, did you get it? Carter, welcome back.
Yep.
Carter, you better not have transferred out of my class.
I definitely did not. So I really like school.
Cool. I'd be very angry. And I'd have a long conversation with you and your parents.
Okay.
Kana, so what do I do first?
Okay, so I just did the rule thing that we have.
So what was the rule? So if I have the derivative, I'm sorry, if I have the function of a to the power of x, then the derivative of that is going to be what?
A to the power of x. And then
Ln of a, yeah. Mhm. Right, so when we took the derivative of the outside function, what do we get?
so 3 to the cotangent of x.
Okay,
ln of b,
nice.
times the cosecant squared of x.
Yeah. Negative cosecant, I can't even write very well. Cosecant squared of x, yeah. Is that what everybody else got? Thomas?
Well, I actually have a question about something kind of different. May I ask it?
Yes?
Well, what is the derivative of x to the power of x?
X to the power of x. Because that becomes x to the power of x is it an exponential function or is it a polynomial?
I have no clue. How am I supposed to know?
Do you know how to check all of your answers?
Calculator.
There is, if you go to Google and you type in derivative calculator, calculator, it will give you, so I really like Symbolab, so I'm going to try, oh, here's a Symbolab right here. So the question is, what in the heck is the derivative of x to the power, if it's going to let me, x to the power of x? So there we go, we get that. Which is, I'm just wondering how that, oh, because in fact, this is, well, it shows you the steps, yeah. Okay, there you go. Are we good with this one? All right, let's do another one. Another example, same thing. We're trying to find the derivative. I have g of t equals t squared times 2 to the power of t. And it's probably obvious, but I'm going to say it anyway. We're finding the derivative with respect to t. What rules do we have to use? Do we have to use the chain rule?
No.
No. Do we have to use the quotient rule?
No.
Do we have to use the power rule?
Yes. Yes.
Okay, we have to use the power rule. What else do we have to use?
Exponential.
The product rule. And one of our new flashcards, the exponential rule. Was it helpful? Did you find it helpful when I rewrote everything like this and then assigned values for f of x and g of x? Or I'm just trying to figure out how to solve for this with you. Did you find this helpful, or should we just do it the shortcut way? It was helpful? Okay, let's do this again. I think it's sort of, especially if you're uncomfortable with these concepts still, I think it's a really great way of minimizing mistakes. So we do see that we have a function times another function. So we know we're going to have to use the product rule. And the product rule says that if I have, I'll move over a bit. If I have some function times another function, then the derivative is going to be what? The first function times the derivative of the second plus the second times the derivative of the first. Yep. So let's assign values for all of this. Based upon our problem that we're looking at right now, what is f of x? Okay, now what's f of x? Okay, it's x squared, yep. What is the derivative of f of x? 2t. What is g of x? Which should not be confused with this g of t. Yep, 2 to the t. And the derivative? 2 to the t. Yep. Ln of 2. And now we just plug and chug, right? We just take these values here and plug them into our product rule. So that gives us g prime of t equals f. F is x squared, t squared times our g prime, which is 2 to the power of t times ln of 2. 2 to the power of t times ln of 2 plus our g of x, which is 2 to the power of t times our f prime of x, which is 2t. If this is a free response, stop there. Actually, I think it's probably good anyway. Trying to think, I could factor that out and that out, but I'm not sure that that really helps. Can't see I can factor anything else out. So yeah, I don't see how we could simplify that anymore. Okay. Moving on. At what point does the function of 2 to the power of t minus 3 have a tangent of 2? At what point does the function y equals 2 to the power of t minus 3 have a tangent of 2? Mr. Hall, you said we weren't going to have to use our calculator. Well, you're not. We're just going to have a perfect answer. We'll calculate a perfect answer. So you don't have to use your calculator. We good? More time? Jillian, what did you do? Okay. And what about the derivative of this piece? Yeah, it's just 0. It's gone. Okay. And then the tangent is our slope. And so we're going to make that 2. 2 equals 2 to the power of x times ln of 2. Okay. So we're trying to isolate our t value, right? So this is times. And really, this is just a constant. If it's just a constant, what if this was, say, 8? What would you do? And because we're trying to isolate t, our goal is to get t equals something. There's no t in this, so let's just divide by ln of 2. I think what gets confusing is that we're dealing with some values that we're not really comfortable with. But yeah, this is just a constant. So we're just going to divide both sides by ln of 2. Yes, sir.
The function of y equals 2 to the power of t minus 3, correct?
This one here.
No, I did it. That's on me.
So that gives me 2 to the power of t equals 2 over ln of 2. Again, our goal is to get t equals something. Jillian. Yeah. If we do log base 2 to both sides, I have log base 2 of 2 to the power of x equals log base 2 of 2 over ln of 2. These are inverses, leaving me with x by itself. So there you go. So, not x, t. T equals log base 2 of 2 over ln of 2. Now, you could say at this point, well, Mr. Hall, you said it was a point. And that's not really a point. Then we could say that this is our x value. What's our corresponding y value? Well, if you wanted to take it one more step further like that, we would just take that value. If I want to know what my corresponding y value is, then I'm just going to cut this. We're getting perfect answers. And we're going to just replace then that t value. So that would give us our corresponding y value would be 2 to the power of log base 2 of 2 over ln of 2. But what's this? Yeah, they're inverses. They undo each other. And we're left with y equals 2 over ln of 2. So the precise point on our curve where we have a slope of 2 is at log base 2 of 2 over ln of 2, comma 2 over ln of 2. Yes, sir. Uh-oh. Oh, yeah. We forgot this minus 3. Yep. So what I did is I took this value here, that was my t value, and I plugged it in for t here, but then I forgot my minus 3. But Thomas reminded me of that, so we have to put that in there. Moving this over. Yeah, so that becomes -3. There we go. Let's see where we are. Ah, our last flashcard. No, 2 more flashcards. Okay. I want to find when I have y equals ln of x, and I want to find the derivative of this. And this is going to look, if we know that y equals e to the x looks something like that, then we know that this function, ln of x, is going to be a reflection across the y equals x. So it will look something like this. This is my y equals ln of x. Now to find the derivative, to find the slope at any point along that graph, I need to come up with my derivative function for this. Now the first thing I want to do to find the derivative function of this is I'm going to solve for x. I'm going to solve for x. Now what can I do to get x by itself? What's the inverse of ln? E to the x. Yep. So on both sides, I'm going to do an e like this. These are inverses. They undo each other. And that gives me then e to the y equals x. Now that I have e to the y, I'm going to take the derivative of this function implicitly. We already calculated this. So now that we have rewritten this, instead of with using ln, we rewrote this with e. Now we can solve for this implicitly to solve for what y equals ln of x is. So remember how to solve implicitly? We're going to find the derivative with respect to x. We're going to find the derivative of y with respect to x. So what does this become? Louder? Nice. It's ey, so the derivative of e to the u is e to the u. But we're taking the derivative of y with respect to x, so we still have this y prime. And then that equals, what's the derivative of x? Louder? 1. Now the whole point of this was to try to find the derivative of this function. So let's solve for y prime. If we solve for y prime, we get what? Y prime equals what? E to the y. Now I really want to solve so that x is over here. So if I want to know if I want to know the slope at any value of x, I just plug in x. Can you see anything up here that we've done before that we could substitute into this equation so that we don't have y anymore on the right-hand side, it's x?
E to the y equals x.
Yeah, e to the y equals x. So what if we plug that into here? So the derivative of ln of x is what? 1 over x. The derivative of ln of x. So that's our next flashcard. So we're going to plug that in. So we get y equals ln of x. The derivative of ln of x is 1 over x. Now, some of you might be looking at this and saying, well, it seems like you could do this with a polynomial. Is there some way that we could rewrite that with a polynomial? Like if I had, is there something? So what I want to do, I'm going to use the power rule, y equals a times x to the power of n, and rewrite this. I'm getting sloppy. The later the day goes, the sloppier I get. A times x to the power of n. Using the power rule, I get a times n times x to the power of n minus 1. Now I want to rewrite this. What would my polynomial be so that I get x to the power of -1? Oh, that was my derivative. What would my polynomial be so that I get x to the power of -1? Wouldn't that have to be something like you guys following what I'm trying to do? I'm trying to go backwards. Yeah, what would, yeah, so that we get the same thing. Is there a polynomial that will give me this? So that would be, well, if I'm going to get a -1, then n has to be what? 0. So that would give me then 0 here. So that would be x to the power of 0. Does that work? Does that take me here? Don't I have to multiply by that exponent? It just gives me 0. Yeah, so we can't. There's no polynomial that will take me here. Do you agree? So we have ln of x that will take us there. And how do we know that ln of x will take us there? How do we know that the derivative of ln of x is 1 over x? Well, we calculated it. We already, this is the proof. Right here, that is the proof. Showing us that the derivative of ln of x is indeed 1 over x. Is everybody good? Okay, let's look at an example. Let's do an example. I have, so same thing, I want to find dy dx. And we have y equals ln of 2 minus cosine of x. Dy dx. What is that? Isn't this the chain rule? Where the outside function is ln of u? Let me write that again. The outside function is ln of u, but u is what? Yeah, so the chain rule is always the derivative of the outside function. Yeah, so I need to multiply this by something. What's the derivative of 2? 0. What's the derivative of cosine of x? Yeah, so I have this negative and I have negative sine of x, which becomes what? Positive sine of x. Good. That gives us a positive sine of x. So you could just stop here if you wanted to, or we could put this sine of x over. So I'd have sine of x over 2 minus cosine of x. Either way is fine with me. Yeah. Be careful with the chain rule. You have to be looking for the chain rule. All right. I said I'm going to give you 4 more flashcards today. The first one was the derivative of e to the x, which is e to the x. The next one was a some base, it doesn't matter, it could be 2 or 5, a to the x. The derivative of a to the x is? Yeah, a to the x times ln of a. And then we talked about the derivative of ln of x. The derivative of ln of x is 1 over x. And the last one, any ideas what the last one is? What about the anything log? What about the anything log? What about the anything log? So if I have the anything log is this. Y equals log base a of x. This is the anything log. The derivative of this, I'm going to actually write it to the side here. This is our last flashcard. The derivative of this is 1 over, I'm going to write it this way, 1 over x. The derivative of ln of x is 1 over x. And then just like when we did our e to the x, or the a to the x, we multiplied by ln of a. But in this case, it's the inverse. So instead of multiplying by ln of a, we're going to divide by ln of a. So we're going to divide by ln of a, and if you prefer to write it this way, 1 over x times ln of a. Using this rule, what is the derivative? Using this rule, what is the derivative of ln of x? Help me out. 1 over x times ln of a, what's a? What's this? What's my base here? Ln is the base of what ln is log base what? E. So what goes here? E. Well, what is ln of e? It's, yeah, they're inverses there. It just gives you 1. So I have 1 over x. So we get the same answer. Okay. I want the derivative. If I have y equals log base 2 of 3t plus 1. I want to find dy dt. Using our rule, right? Here. What do we get? One more time, what is it? We have, if I have y equals log base a of x, what does this become? Y prime equals 1 over x ln of a. Okay. So what is this? Do you guys see the chain rule? Yeah, because this is log base 2 of u, and u is 3t plus 1. So what do we have? 1 over 3t plus 1. Yeah, ln of 2. A is 2, so ln of 2, there you go. Actually, there's a mistake. We still have to do the chain rule. You're correct. We still have to do the chain rule. So what are we missing? Times 3. Yep, now we're correct. This is the answer. If you want, you could, if this is free response, just stop. If it's not, we could clean it up and have 3. Remember, 3 over 1, we're multiplying fractions, numerator, multiply the numerators to get a new numerator answer. We multiply the denominators to get a new denominator answer. So that'd get us 3 over 3x plus 1 times ln of 2, if you wanted to clean it up. And if it's free response, just stop where you don't do extra arithmetic where you could possibly make a mistake. Even if you're confident, I think it's just safer to just stop. Okay, we're good? Okay, let's do another one. Same thing, I want to find the derivative of y equals 1 over log base 5 of x. Anybody think of a strategy? So you want to change this to y equals log base 5 of x to the power negative 1. Is that the same thing? And what if we do all of it like this? Okay, what do we get? This to me looks like the chain rule. What's the outside function? Yeah, the first one is the outside function is u to the power negative 1. The inside function is log base 5 of x. So the outside function, we have what? The derivative of y, or the derivative of the function derivative. Y prime is negative u, which would be log base 5 of x to the power of negative 2. Yep. Or don't we just multiply by the derivative of the inside function? Let's review this. We have y equals log base a of x. The derivative of that is going to be what? 1 over x times what? Ln of a. So what's the derivative of this? One over x times ln of 5, yeah. Yep. So we took the derivative of the outside function, which is here, times the derivative of the inside function, which is there. We're good. Yep. There we go. All right. I want to know what the derivative of sine of x is. Cosine of x. Don't you think this is a weird class where almost all of the math that we're going to learn is shortcuts? It's weird. Okay. What is the derivative of cosine of x? Negative sine of x. Yep. What is the derivative of tangent of x? Secant squared of x. What is the derivative of cotangent of x? Yeah, because this is a co-function, it has to be negative. This is negative cosecant squared of x. What is the derivative of cosecant of x? Yeah, it's another co-function, so it will be negative cosecant of x times cotangent of x. What is the derivative of secant of x? Secant of x times tangent of x. Good. What is the derivative? Oh, sorry. What is the limit as x approaches 0 of sine of x over x? It's 1. Good. What is the limit as x approaches infinity of sine of x over x? 0. Good. What is the limit as x approaches infinity of cosine of x over x? 0. What is the derivative of the inverse of sine of x? Nice. 1 over the square root of 1 minus x squared. Nice. What is the derivative of the inverse of cosine of x? It's negative 1 over the square root of 1 minus x squared. Nice. What is the derivative of the inverse of tangent of x? Yeah, 1 over x squared what? Plus 1. Good. 1 over x squared plus 1. What is the derivative of the inverse of cotangent of x? Yeah, it's the same one as the tangent one, but it's negative because it's a co-function. So we have negative 1 over x squared plus 1. What is the derivative of the inverse of secant of x? Yeah, this one is one of the hardest ones. This is, it's not a cofunction, so we know it's positive. This is 1 over the absolute value of x times the square root of x squared minus 1. There we go. All right, what about the next one? What is the derivative of the inverse of cosecant of x? Nice. It's a cofunction, so it should be negative. -1 over the absolute value of x times the square root of x squared minus 1. There we go. All right, these are the new ones that we learned today. What is the derivative of e to the x? It's e to the x. What is the derivative of ln of x? 1 over x. Good. What is the derivative of a to the x? Yeah, it's a to the x times ln of a. Nice. What is the derivative of log base a of x? Yeah, this is 1 over x times ln of a. There we go, and that's all of them. Now, if we wanted to mix this up, I know we don't have a lot of time left, but again, I really encourage you, please go to these flashcards. If you don't feel like you can handle all of the flashcards at once, do the beginner level or the intermediate level. The advanced level has all of them. So this is actually a video that I put together of those flashcards. You cannot find this anywhere except here because I created it. Okay. Advanced flashcards, AP, calculus, AB. All right, what's this one? We have to go fast. We only have about 2 minutes. Okay, try to say it fast. Here's the next one. Is that too fast? Okay, you can always pause it. We can always pause it. If it's going too fast, please pause it. Okay. Okay, I will go slower. I will go slower. Okay, let's go back. Okay, what is the derivative of the inverse of cotangent of x? Nice, good. What is the derivative of ln of x? 1 over x, good. I don't think I had to pause up. I don't think I had to pause that one. I think you could have done this one. What is the inverse of sine of x? Or the derivative of the inverse of sine of x? Nice. What is the derivative of sine of x? Yeah, cosine of x. What is the derivative of a to the x? Nice. What is the derivative of cosecant of x? Yeah, I think I said it wrong. It was the derivative of the inverse of cosecant of x. I think I said that one wrong, but you guys said it right. Good job. What's the derivative of secant of x? Secant of x times tangent of x. Good. What's the limit as x approaches 0 of sine of x over x? 1. What is the derivative of cosine of x? Nice. What is the derivative? Oops, sorry. What is the derivative of the inverse of tangent of x? 1 over x squared plus 1. Good. E. What is the limit as x approaches infinity of sine of x over x? What is the derivative of tangent of x? Secant squared of x. Good. What is the derivative of e to the x? What is the derivative of cosecant of x? Negative cosecant of x times cotangent of x. Is everybody releasing already? What is the inverse of the inverse of cosine of x.